Yes, sir.
Okay, okay. Did you work out any problems on those streamlines, streak lines, all those things? For some examples, for the exam sake, you have to do whatever what you can write for the exam. So whatever I'm teaching. So right now you have only how do you find those streamlines, streak lines? Okay. So and then derivation of these equations. Of course, you are only dealing with the ideal fluid as of now. There is no viscosity. Slowly, I think we'll before exam we'll try to do some special cases like finding the steam function. Yeah. Yeah. Before this mid-sem, when is your mid-sem exam? September, which day?
Sir, from 15 September, sir.
15th September is our exam.
Yes, sir, from it started, sir.
No, from okay, but when is this exam?
So we
Mid.
haven't,
Sir, and
so we haven't
it,
received the table yet.
the,
Oh, we
till
have to
now,
fix, right? We have to fix. Do we have to fix or they will fix the date?
yes, sir.
Teacher will fix. So we'll consider
Sir,
that last date.
examination cell will be fixed. Yes.
Oh, they will decide. Huh? So okay. So if it is in our
Okay,
hands,
sir.
we can fix it the last date of your examination week, so that you will have sufficient time and sufficient
Uh,
material.
we
Huh?
Yes, we can told to our faculty advisor to fix
I
this
will
exam
inform.
as a last date.
Yeah, Nikhil, I'll
Okay,
inform.
okay, sir.
So that's enough
Okay, sir.
material will be
Okay,
there
sir.
for the mid-sem, so that continue. Similarly, up to sometime in October, I may visit. So we'll have interaction. So whatever is happening that time, we'll see. We'll have direct classes. Okay,
Okay,
so
sir.
sometime in October, before Diwali, I guess. And then I think I'll come and conduct the final exam. So sometime in November, I'll come again, one more trip, so that we can finalize the courses. So all are here? Not. We can start, or some will join. 2, 3 at
Okay,
a
sir.
time. So you can start, right? So this you see this question, no, this P n cap integral d dou w P n cap ds. That is not actually by Green's theorem. So how do we prove that? We'll see. Okay. So we'll see now how we do that one. So let's see. Do those calculations. Okay. So what we need to show is integral dou w. What do you have this? There you have a pressure P at n cap ds. ds is basically a scalar surface. Okay. ds is like a scalar surface area. Okay. Not like vector surface area. So this one, to see that this is equal to, what did we get? Integral. What did we get? So this is equal to, so what did we prove? So we converted directly into this divergence of P n cap dV. Okay. So this is we need to show this one. Okay. So this proof is what we do is basically uh, you start doing some arbitrary, let V be an arbitrary fixed vector. Okay. Let V be a fixed vector in R3. So when you do this, you try to take a dot product with this. So you take a dot product with this one. So E dot V dot, make a dot product with dot W P n cap ds. This is equal to dot W V dot P n cap, right? That is your vector. This is a scalar. P is a scalar. So P V bar dot n cap. Okay. ds. This is together, you can put it. So now you can apply your divergence theorem. So this is by divergence theorem over W del dot. So you need the divergence of a vector field. Now this is your P V. Okay, so this is it. Now this is by divergence theorem. So what is this one? Now if you do it, this is simply W. Now if you expand this one, gradient of P dot product with V dV plus W. What else you need to do here?
Gradient of V with P.
P times divergence of V, right?
Gradient of,
So it's a
yes,
vector.
yes.
It's a vector, right? So this is dV. So this is 0 because V is fixed. Is constant vector. Okay, constant vector. So if you use this one, so this is 0. So what you are left with only this one. So this is what we wrote. So this is like now this is a constant vector. Take it out. Take it out. Integral W dot product with gradient of P dV. So that's what you want, no? This is true for every V. So implies gradient of P. What happened N? N I think we missed now.
Yes, sir. That's my doubt, sir. Where is N gone, sir? Here, when we apply
N is not there.
divergence theorem, then I think N
I
is
think
also here.
N is also there. No, it is not N. I guess it is. It should be. I think I made a mistake. That should be. Okay, so I think without proof we have done. So let's see. So this will give me this one, right? So V dot this equal to this one. So this implies. So the without proof we have done the dw p n cap ds. This is a vector. There's already a vector here. So w gradient of p is a vector dv. This should be the one. So you don't have anything dot there. So there is no like. It's simply gradient of P alone. Okay. This should be gradient of P dV. This is what we need to show. Okay. So if we go back and put it there, I think that we need to correct that previous thing. So previously what we had is you need to correct. You substitute this one. So if you substitute this one there, so what you have is that force is equal to minus integral W grad P dV, right? I'm not putting the 10 cap. So go back when we put that question mark there, right? So that one I think we put without n cap. Followed? So there's no n cap. So this is the correct thing. So not dot Dot n cap means
Yes,
it's a
sir.
vector. It is scalar, right? So now it is vector. So it's fine. So you remove that one, n cap, in the wherever I put the question mark in the last lecture. So you end up getting now the less. So this one is external forces. You have W rho. This is density outside external forces or something like B, vector field B or dV. Okay. So this is your force, which is equal to MA. MA, we already know that this is over W. M A is acceleration, that we already know that this is a total derivative of u bar by dt. Okay, dv. This is your MA. Okay, this is your force. So this will give me finally integral W over W rho d u by dt plus equal to just plus, make it plus, gradient of P minus rho B bar dV equal to 0 for every W. What is W? W is arbitrary domain, right? Fixed domain. Fluid element. W is a subset of R3. So for every W3, so this implies that inside integrand has to be 0. That is your basically your differential form of momentum equation. Okay. So rho times du by dt. I'll just try to like minus this. I take it. This is equal to 0 minus grad P. This is going to be plus rho times B bar. So this is your momentum equation in differential form. Up to here, any doubt? Hello? You see, you always fix one way of deriving. Okay. So far you have derived mass equation, and this is your momentum equation in differentiable form. Differential form means you are under the conditions that you can apply all these different derivatives exist, right? So to apply this divergence theorem, all the conditions under which only you can do, so that what you get is your differentiable form. Differential form of this momentum equation. Where is the momentum here? Okay, so we can, you may not see exactly that way. So it's like F equal to ma type. There's also momentum, but to get a simplification nicely, we will see how we get this one. Okay, so what we do is we try to write like this further. Okay, so you may see in a different form. So rho times what is the total derivative of u? That is your dou u, right? Dou u by dou t plus what is that you need to put? Rho into, yeah, u, right? This is the vector usual uvw dot product with dou x dou y of u, this u. Okay, so grade this del operator acting on u itself. Do you understand? So u times dou u by dou x plus v times dou v by dou x dou y and so on. That's what you get. Okay, so that's what we replaced here, equal to minus del p plus rho b. Now what you can, so if I use my equation of continuity, what is your equation of continuity that you derived last first equation? What is your equation of dou rho by dou t, right? What is your equation of continuity? Dou rho by dou t plus del dot rho u bar equal to 0. Okay. Mass equation. Okay. So what we do? How are you going to apply here? So I'm going to use this one. Okay. So this, if I use it here, so this will give me rho dou u by dou t equal to minus rho bar del acting on u minus del p plus rho b bar. Now what do you do? What is your equation of continuity? Dou rho by dou t only, no? Hello? So this is,
Yes, sir.
this is your equation of continuity, no? So you can expand it. Okay, so what do you do? What you can do there?
And gradient we can expand.
So I'll try to write like this. So okay, just keep in mind this one. I will not yet use it. So this is your equation of continuity. Okay, so that we will do something. So we'll try to do something here. So what I do is you'll see this one. So dou t of rho u. What is its value? This is equal to dou rho by dou t u plus what is the other one?
Sir, rho into
Rho
dou
into
u dou u
dou
by
u
dou t.
dou u by dou u by dou t. Dou u by dou t, right? Is it dou u by dou t? Yeah. Okay. So
Yes, sir.
what is exactly on the left hand side is basically is your momentum, rate of momentum, right? Rate of change of momentum. It's time dou dot t. Okay. So this is what I want in your equation here. So if you replace this one here, since this is this, now dou rho by dou t is what from the mass equation I can replace, right? Dou rho by dou t from this equation. So that will give me minus del dot rho u bar, okay, into u, right? This one from the mass equation and u as it is plus rho times dou u by dou t, rho into dou u by dou t. I can now replace this with this. Okay, followed? So
Yes,
minus,
sir.
so this is minus rho into u dot del u bar minus grad p plus rho b bar. So remove this hints. Can you see this now? So using this, so you want basically you don't want this one. This is not giving you exactly the that momentum rate of change of momentum, right? So momentum equation is basically a rate of change of momentum and should be on your left hand side. So this I'm replacing is like on a fixed domain. So if you say dou t of rho u, why on the fixed domain? So let us say if you are watching only spatial domain, what is this ddt of some quantity? u dv equal to is over w dou u by dou t dv, isn't it? This is what is happening, right? Because omega is fixed, w is fixed. Fixed domain means rate of change is basically it gives you only time variations. It's not we're not following the particle. Okay, so as though x y z are fixed. So this is same as dou only time variation only was see. Okay, this is what this you already used in your mass equation. Same thing, right? So if you actually see this mass equation in the last class, that's what we did. ddt of mwt is ddt of w rho of xt dv equal to what do you have? So dou rho, we wrote inside dou rho by dou t. So basically we use this one. Okay. So we use this one. So that's what we wanted. For that reason, we wrote like this. So now go and put your, what do you want to put? So we are now going in a reverse way. Okay. From that equation. So you try to put it back into that. Okay. Now what, how to put it back into that integral form. So we are doing again like you take the dot product. Okay, I take the dot product with dou dot t with any vector v. Okay, for a fixed vector v in R3. So I take a dot product with this dou dot t of rho u. What is that you get here? So this is what here, right? So first quantity.
Sir, v dot dou
Let
rho
me
by
write it.
dou
So
t
minus del dot rho u into u dot v. Okay, that's your first one. So dot product one, So that's your dot.
v dot u.
Minus where is v? V dot u or u dot v both are same, no? So you can put it here v dot u or u dot v both are same. So if you want v dot u, okay, v dot u. Okay. So the next quantity is here. So that is rho into u dot del times again v dot u here, right? And then here grad p dot or v dot grad p plus rho into b bar dot v. This is what you do for every b. Okay. Now try to simplify here. So if you simplify this is what happens here. I'll have a minus del dot. So what is inside? Inside, I'm going to put this first PV. Okay. P comes out del dot V, right? Grad P dot V means what? Is it there? What is that sound? Someone wants to join. Okay. Can you see here? See, what I'm trying to do is first you see that grad P dot V is same as dot product. Okay. This dot product is same as del dot PV. We already used because V is a fixed vector, right? Because del dot V is 0. P into del dot V is 0, right? This is actually this is equal to 0. So that is the reason I can replace this with this. So I will have del dot PV for this one. Okay, that one. And what else I can replace? Okay, this I now I'll replace. So this is plus rho u v dot u What else is left? This is left, right? Del dot. I think this together we can put it like v dot u comes out common, and what you have is del dot rho u plus rho into del dot u. Del dot u or u dot delta both are same, right? So this is an operator, isn't it? Hello? Dot product you can always do, no? So dou x u into dou x, that's an operator acting on this.
Yes,
So
sir.
that's this is same as this. This is a vector, right? So this, if you put it, so use this one. That's what we wrote here. Can you see? Del dot rho u. Del dot rho u of v dot u. Is this correct?
Yes, sir.
Del u v dot u. So if you take this del dot u, this is what you have. So basically that one. So you see that one. You'll see you actually see that these two together is this one. Identify. Okay. So this is one, and you are left with without any del. What you have is rho into b dot v. Okay. So now you put it together. This is like v. You take it out. Del. So if you take it out, what is that you are getting? Okay. Now put it back into yeah. Since v, this is true for every v in R3. So what do you get here? Dou t of. So okay. So you try to use. I'm not directly getting anything from this. I'll try to put it in this setup. So in this setup, you have dou t right here. So you have dou t inside, right? You have inside dou t. So right now I have only dou t here on the left hand side. Dou t dot v, right? So that you want it to go inside. So I'll put that. I can write it like a left hand side. Ddt of over. Okay, let me write it. So see that both are same. What happened? I'm going to write it like dt of integral over w rho u dv. What is this one? This is actually dot v. Okay, so with v dot v also I'm going to put it. So because you have v here, so let me put it v dot this one. This is same as this only, right? So this is same as v dot integral w dou rho u by dou t dv. So this is same as integral w v dot dou rho u by dou t dv. So this is what is your left hand side. Okay. So this is what I wrote it as v dot ddt of this. This is equal to, now what is that I do? Now I'm going to replace here. So the right hand side. So whatever right hand side here, if we do, this is over w v dot. So what do you have here? Minus delta del dot with pv plus rho u v dot u plus rho b dot v bar dv, isn't it? In the place of this, I put it. Okay. So what is this one? Now what do you do? I'm going to convert this del dot thing into surface. Okay. So over the surface, if I put it, what is that you get? If I do the surface, back to again divergence theorem. So if I use this dou w del dot, the whole things up to here. Okay. Only here we have del dot. This is different. Okay. So this is only for this side inside. Okay. Not for rho b v. Okay. So that this is another term. This term is different. So this you can apply your divergence theorem to see that minus dou w. And what you have? P. What do you write now? Del dot PV, right? So P, what do you write here? Del dot PV, just now you have seen, no? So we showed in the just now here. Del dot P dot P. You try to put it as a dot V both sides. What is that you get? V dot gradient of P is nothing but V dot P n cap. So that you can replace. Okay. This one you put it. So go back and put it. Del dot P V. This becomes P n cap ds, isn't it?
Yes, sir.
Similarly, minus another this term I'm writing. So dou w. This is anyway. So there is nothing here. See here also you see that rho u v dot u. This is your vector. So I'm not changing anything here. So this whole vector I'm taking a dot product with n. Is it a dot product? It is, right?
Yes, sir.
That's your basically divergence there. So you have a divergence from del dot f. This is like fully f dot n ds. Okay, over dou w, and this becomes this I'm writing as it is. W rho b bar w v bar dv. So this is what is your v dot ddt of w rho u bar dv. So this is true for every v bar in R3. Now I can remove that v, right? So I can just remove that v, so that what you get is ddt. So the rate of change of fixed w. This is your momentum dv equal to minus dou w. So what is that inside? You have p n cap. Now I can put them together. So plus that v I am removing. Okay. If you remove, what is that? What is left? Rho u bar dot n cap. That is what is your vector, right?
Yes, sir.
So rho u into, yeah. So that's anyway. So you can remove that, no? So if you remove, what do you get here? What exactly you will get? Tell me. Rho u dot n, right?
Sir, two times U is there. Now, if we remove V, then
That's why. See,
is there
you
two?
put this outside. You put this outside. This is just a number. V bar dot
Okay.
u bar. V bar
Okay.
dot u bar into rho u bar dot n cap ds, that you put it as it is. So rho u bar into the dot
Dot.
product. If you remove that u comes out, right? So
Yes,
that
sir. Yes, sir.
so I'm going to put it like for you to understand. V bar dot u you write. Okay, so v bar dot u bar, that makes it like once you remove that v bar both sides dot dot, then it will be rho u bar. Okay, and then what you have is rho u bar dot n cap. This is what this with n. Okay, ds. Understood?
Yes, sir.
This I put it outside. So on this one plus integral w. This is any external force b dv. I removed that v dot product. Okay, so this is what is true. So this implies again now if you write it ddt of this is rate of change of momentum in a fixed fluid element w dv equal to minus dou w p n cap pressure n cap plus now this is a constant, right? Dot product. So rho I can take it out. I'm not doing
Yes,
anything on
sir.
that. So
Yes,
take it
sir.
out. So rho u bar into u bar dot n cap ds. This is only surface area element. Okay, so this one plus integral w rho b bar dv. So what is that you derived right now? I have not used any. This is some kind of we sometimes you see we assume all the differentiability and try to derive put it in the integral form. So you're not supposed to use this integral form without using that the conditions of the divergence there. But we have already used inside to derive this one. We already used the divergence theorem. So all the conditions we are assuming that it is differentiable. Okay, but still it is valid, right? Suppose you have integral form without without it, they need not be differentiable to apply your divergence theorem. Okay, so that is how you have to generally derive the integral. So this is actually integral form of equation of motion. Okay, momentum equation, momentum equation, momentum equation in integral form. Integral form. So what you how you are supposed to derive this is without using divergence theorem. But here we use the divergence theorem. Okay, and then we use the mass equation also. Okay, so mass equation when you derive, so finally what you are getting is same equation. This is actually integral form. So the rate of change of momentum left hand side, right hand side is basically your surface forces, fixed fluid element w dou w on the surface through the surface. This is your what is this one? This is actually your flux, momentum flux. Okay, this is called momentum flux. So we'll write this p and cap. Whatever, see, this is basically rate of change of momentum, right? In a fixed volume W. Now, what is this? Whatever from the surface, this flux, whatever goes out or coming inside through that surface only is possible, right? Like mass in a volume, whatever comes in, how it is coming. So it's coming through the surface. So similar way. So this is actually the quantity that is inside here on the right hand side. First one, rho u into u bar n is actually momentum flux. Flux through the surface. Okay, so this is inside the ds, no? So per unit area. Per unit area, you can say. Through area you're getting, no? So through per unit area. Or the whole right hand side, this first thing is you say that it's a momentum flux through the surface dou omega. Okay. So if you put the integral, there's actually momentum flux through the surface dou w. Dou w. I was sometimes calling omega. That's actually w. Okay. You understand now?
Yes, sir.
So that is what it is. So and also it contributes through this external forces also. That B is external force, right? So this is actually integral form of momentum equation. Okay, but here we used divergence theorem, all the conditions of the divergence theorem. Any questions up to here? You try to follow what my derivation or some derivation. Okay, so this derivation, what I'm doing is purely mathematically I'm deriving. So how I'm deriving? First you derive your see through the differential form of momentum equation I derived first. Okay, so that's what is this one. This is also momentum equation only. Okay, this is easy to remember actually. This one, if you see this one, this is actually. But you may not. So why I'm doing all that integral form is because you can easily clearly see that mv is the momentum. So rate of change of momentum you can see there. So here what you are seeing is not that one. So if you follow the particle du by dt, this is like a force. Only left hand side looks like ma force. Right hand side is basically kind of ma. Okay, our left hand side is ma and the right hand side is actually forces. Okay, that's how you get this one. These are the forces. So force is nothing but force per right, external forces act as the momentum flux also. Okay, so that's why you're seeing the in your second equation, that's an integral form. You see that left hand side rate of change of momentum. The first term is momentum flux going through that surface, and plus some external force, that is the external forces. Okay, that obviously rate of change, this is also whatever flux, momentum flux is also kind of rate of change of momentum only. And this together is basically some influenced by that is same as some external forces. That is same as force, no? F equal to me, fine, ma I see it as rate of change of mv. These are all equivalent things. So throughout what I used is divergence theorem. Sometimes you might have seen in vector calculus and some calculus, you want to derive something integral form. You assume all the conditions of for simplicity, all the conditions of differentiability. If you assume, you will derive the same thing. So that's what we derived. This whatever you derived here, we can derive same thing without using the divergence theorem also. That's what we will do next. Okay. So what exactly you got here is basically the originally is uh, ddt of 6w rho u dv equal to, what is that you got here? So what is this one? Minus of that integral. Whole integral is basically momentum flux. That if you actually see surface forces, right? So initially what is that? F equal to ma. What is F? F is possible by surface forces, that is normal stress, right? Because you're now deriving equations only for ideal fluid. That means there is no only normal stresses are available. So through those normal stresses means that is your pressure. That is the pressure, right? Normal stress means what? Normal force acting on the fluid surface element, fluid element surface. If you see, that is only pressure. P into n cap, right? That is the pressure. That is the force. So that you integrated over your full surface, d dou w. Okay. So that if you see, that is your surface forces. Surface forces. So we write it as I think we wrote like something like this, right? Surface forces, right? SW. Did we write like that earlier?
No, sir.
I think we wrote it last time. I'll show you. We write now F dou W we wrote. Okay, so F dou W. Yeah, we wrote like F dou W. So this is like F dou W. I think we need to be plus external, right? This is your force external. This is your force external. This is actually whatever this first term, momentum flux through W is nothing but your, this is your momentum flux through dou W. Okay, this is external force. Momentum flux through dou W is same as force through forces on dou W. Both are same. Okay. So this is actually rate of change of momentum, or what is this one? This is actually your MA, right? This is also force only, right? Finally, this is also force only. So forces basically you make it equal. So this is what you derived your integral form of the momentum equation. This one, either that one or this one, both are same. Okay, so there I have not used any divergence theorem. Okay, so instead, so if I so far I used only W as fixed one, like Euler variables. You watch only fixed W, fixed fluid element W. Now I'll try to see that W is actually varying with time. Okay, same equation is valid, right? So this is like a primitive. This is your fundamental primitive kind of integral form. Okay, this is a basically fundamental principle. F equal to ma, Newton's first law. Okay, so this is what is actually this one. This is your first principle of moment, first principle of uh, first principle of conservation of momentum, right? Or equation of motion. This is your first principle. So W, if you fix it, that's what we have done so far. Like your equation of mass, we derived differential form of the momentum equation. That is your rho into total derivative of u equal to minus grad p plus external force. Okay, and through the derivation, by the use of mass equation. Okay, and divergence theorem, we derived same equation in a integral form. Okay, this is actually without using the divergence theorem, you're supposed to use this one. Okay, so mass is also conserved. So together we applied, right? So this the same equation, this equation, if you don't use the divergence theorem, so how we derive, we will see. Okay, for that, through this first principle of conservation, but this is what we use. But now what I do is W is varying. So what I do is now W is varying. So how do I put this one? So if W equal to W of time, or W depending on time, so we call this notationally, we say it's WT. Okay, then the conservation of that first thing is the ddt of total rate of change of WT. Now W is actually you're moving with that fluid element. Okay, with time it's the rate of change of the momentum as you follow the fluid particle, like in the Lagrangian. Okay, so if you do this one, rho u, that is what is inside, right? dv. This is same as again F dou WT plus external forces. External forces, if you want, you can write WT rho B bar dV. That's what we wrote now. External forces, right? External forces means this term, rho B bar dV. Okay. So how I'm going to do this here? So what will happen to this first one? So left hand side. So we will do this way. So do you have class next class? We can continue for
Ye-
at least half an hour.
Yes, sir. We have class from 12 to
There is
1,
no
sir.
class, huh? It's
Functional
okay. It's okay.
analysis, sir.
Just 5 minutes. I'll just try to give you put
Okay,
this
okay, sir.
picture and
Okay, sir. Okay, sir.
W is
Uh,
this one. This is fixed. This is your W. Okay. Initially W. Okay. Let us say a fluid at rest. Okay. At rest. Now this is your WT. At time T. W at time T. So that is your WT. Okay. So there is a transformation here. So what is the transformation at every point X bar? No, X bar. If you see what happens to this you call this sum of C. C is your mapping. Okay, there is a map that takes this value X to some value X here. So what happens here? That is fixed there. This is X of T, isn't it? X, this fixed point X will become X of T, right? I'm calling X of T. Okay. So what I'm doing is X bar going to under this X bar T. So how do I put this one? F T is a map from Rn, fixed Rn to then fixed Rn such that, what is that mathematically, right? Phi of x, x is a fixed vector, okay, equal to phi of x comma t. You understand? This is what you have. This the map goes like that. For every x, you give the value x. This is actually taking this one, or rather x of t. Okay, so x of t. So you should put it like x of t. That will be easy for you to understand. So x of t. Okay. So this whole thing, I'm going to represent it like p of x of t. X goes to, so x is going to, x is going to x of t. Okay. It is just a notation thing, so you don't have to worry. So mathematically, looks like a small x, capital X at rest is going to x at time t, so some other variable, because you are moving with the fluid. So you are changing the spatial space also, spatially and time, both you are doing. Okay, that is why this t. So what you have to do? Hello,
Yes, sir.
so you understand now? So this is the map that you do. So it is
Yes, sir.
also moving. It is also moving with time as well as moving with x also. X of t, x of t comma t. So you have to put it like x of t comma t. Okay. So I'm going to put it like yeah. So how do I put it? So p. Yeah, that's okay. So I think this is fine. Okay. This is your. This is what you are doing. So x of this is basically x of t. What is that you have here right now? This is equal to, what is that exactly you do? P of x of t. Okay, not phi. There is no phi, right? So already you removed it. So that's basically both are same. So this is what you are happening. So what I do now is that you try to apply here. So now the left hand side, now W is no more fixed one. So total derivative of the momentum. Total derivative of momentum, it becomes what? If you go with the thing inside. So I'm not going to use yeah, what is that you do? The W is fixed. What it goes is dou rho u by dou t only, right? Now WT is there, means actually this is equal to what? Left hand side. This is equal to total derivative, right? Going
Yes,
to be
sir.
total derivative. That's going to be total derivative. So we will not see physically, you know that it is actually total derivative, but we will see in a different way. So we will try to use the change of variable formula mathematics. In mathematics, we use the change of variable. This is your transformed domain WT, and we'll put it back to the transformed domain. So old domain, so previous domain W. So that is actually where you use the change of variable formula involving the Jacobians. Okay, so that I think I will do next class. So what happens is that just I'll try to write it, so and then leave you here. So DTT. Or you want to go? Is it a physical class, or you have to do online only?
Online class, sir. Online.
Okay, just two more minutes. Huh? So row U.
Okay, sir.
This is what you have into dV. This is equal to. Now what you do is uh, I'm going to put it this as a ddt of integral. Now I am going to change this to change of variable form. If you don't change of variable formula, what will happen? You are actually going back and forth from this. And this is also okay. Both sides is like it should be possible, and the Jacobian should be non-zero, right? The modulus of the Jacobian should be non-zero. So what are the variables here? X, Y, Z goes to this phi of xt, right? So this phi of xt, x comma t. This variable, let's call this after this change of thing. So you call this is again in the space only, right? You call this zeta eta of xt, okay? Eta of xt and zeta eta some other variable, okay? Zeta of xt. This is zeta, there is xi, right? Xi of xt, eta of xt is like this belongs to R3 at time t. So this is like a notation for you to understand mathematically. If you put this, So you know exactly what is your Jacobian. Jacobian should be, what is that you have? Zeta x, zeta y, zeta z, and similarly eta x, eta y, eta z, right? And similarly zeta x, zeta y, zeta z. So this is your Jacobian. That should not be 0. So if you put it this one here, so now it is over W, fixed domain. You're actually putting back to the old this thing. So if this means this should be a rho u. Now where is your rho u point? U at WT, right? This is at x bar of t after time t. So now you're going back to at rest. Rho u bar at, now if you want to rho thing, no, the fixed means if you want to use this transformation x bar t. Okay, now x is only on the fixed domain W at rest, comma t. Okay, and this is on not only this u is only function of x, y, t and t also, right? So if you put this, that is comma t. So this is like, you are in this u bar of x, y, z, comma t, right now. That is what it is. That is what you have. And then what else? What you need to put the Jacobian, right? Jacobian where? Jacobian should be finally function of x, y, z because w is fixed. So it should be zeta x. Zeta is function of xt, so that is zeta x, zeta y, zeta z, zeta x, zeta y. So j is actually your x bar t. With time also, no? It is varying with time, no? Zeta is function of t. Eta is also function of t. So finally j is function of x comma t. X belongs to this w. This is over dv. So this is what we use. This is by change of variable formula. We use this one to derive the same thing, whatever we are saying, no? So this left-hand side, the left-hand side is rate of change of momentum. We could have written directly that, this is actually, we don't know as of now. Okay, so we will see. Okay, so another important thing that we use here is, just think over. So in the dou t, for example, so dou t of this rho u. So what happens? This one. So now once w is fixed, this whatever ddt becomes goes inside is the fixed, no? That becomes dou t, right? Dou t of rho u of phi of xt t. Of course, j also will be there. J of xt. This whole thing inside. This is what it becomes, right? Dt. That is what is the RHS here. So whatever here, that becomes this one. So anyway, so I need not write RHS. So this is what it becomes. Okay. So dou t of any quantity here. Forget about this j. J you leave it. What is this quantity? Now you are moving with this is the time derivative of what is that rho u? That is the fluid property. That is u. Rho u bar is your fluid property, and you are moving with the time, moving with the flow, right? So what is the rate of change of time? If you are moving with the time means what? That is the total derivative, right? Though you are writing dou t of this one, this is nothing but your ddt, right? ddt of rho u bar, because you are moving with the fluid, right? X bar of t comma t. T is there now. Both in the spatial also you have t time is varying. That is the reason. Do you understand? Into this is into j of x t. This is into dv. Okay. So of course I didn't put the integral. Yeah. Now we have the integral w. Try to understand up to here. Okay. Next class tomorrow we will see how we are going to derive this one. So now we use this one total derivative. You act on these two. For that we need total derivative of j also. So that is a lemma we use, and then we'll see. Okay, so we'll derive that momentum equation in integral form without using any divergence theorem. That is actually actual way to derive your integral form of the momentum equation. So this is the equation, though momentum equation. It's like you derive simplest equation, actual equation in simplest under simplest assumptions, but finally it will give you same, no? something similar here. So you are assuming that all are differentiable. All the functions here are differentiable, so that you can use your divergence theorem and you derive this quantity. So the same quantity without using that divergence theorem, we use without using that you derive this one. That is what is actually called integral form. So why do we use this one without using divergence? Basically, it's an integral form means it is not differentiable. All the quantities inside, if you are not sure about the differentiability, then you have to use the integrable form of the equations. If it is smooth inside all those whatever quantity fluid properties that you are if they are smooth, then you can use their difference. You can work with the differential equation. Otherwise, you'll have to deal with if there is a singularities or there is a uh, differentiability. Suppose you're losing the differentiability. So that is where you use the integral form. Okay. So I will see you next class tomorrow.
Okay, sir. Thank you, sir.
We'll see you at 10. Yeah, 10:15. We'll see you again. We derive the same thing without using divergence there. Okay. Bye.